I like to start talking about this small phrase that is civilization advanced by extending a number of important operations that we can automate. And I guess 2023 is going to be known by the year where we start to automating more and more things. I really like that Vanessa introduced a word that I'm going to be going over and over in this talk, that is abstraction. And my talk is really a build-up of everything that I'm working on right now. But I wanted to introduce the topic of abstractions. Like, why are we here? Why are we talking about HPC on the cloud? And to me, it's a personal view. It's all about abstractions, right? We started with Linux many years ago, almost 30 years ago now. But we have been building layers of abstraction over and over that, to the point that today we all talk about Kubernetes, right? Like, if you want to use Linux for HPC, you are going through Kubernetes, and that is abstracting everything under that. And what is really abstracting? It is abstracting the operating system. It is abstracting the virtual machines or hypervisors. Today we call that containers. It is abstracting multi-cloud when we want to use Google and Amazon all at the same time. Right? Like Kubernetes is really becoming that next level of abstraction, and things that, like Qflux, the project that Vanessa and Claudia just introduced to us, is a next level that is what is going to come on top of Kubernetes, and that is being enabled by the controllers, as Vanessa really said. A little bit of who am I, for those who don't recognize me. My name, Carlos Eduardo Arango. I'm from Colombia. I have a really quick roadmap into HPC. I started working in HPC with Scilabs. I was part of the initial crew of Singularity, as with Vanessa. Then I moved to the Kubernetes world, working in OpenShift, mostly in the HPC side of OpenShift. And now I'm part of NVIDIA, where we are building a cloud-native team for all things related to utilizing NVIDIA machines and everything that is AI, ML, with NVIDIA GPUs, but from the cloud. As you have heard many talks from Jensen Huang, he's always saying, like, NVIDIA is going to become an all cloud native company. Well, I'm working in a team that is called Cloud Native inside NVIDIA. So today I'm going to be talking about three very important topics that my team is working on, that is really to enable the utilization of special resources like a GPU from Kubernetes, right? For those that are already trying to use HPC with Kubernetes, you can tell that using things like FPGAs, accelerators, not just NVIDIA GPUs, but Intel GPUs or other specialized hardware that is very custom for HPC, utilizing those resources from Kubernetes today is very cumbersome, very hard, and you have to set up a lot of things as a system admin before actually getting to utilizing them. And then once you need to do an update or you change a dependency, everything breaks. So we have been working with companies like Intel and other hardware vendors to facilitate the way that we can consume a specialized hardware. During this talk, I'm going to be making it easier in just saying GPU, GPU, but really put it as FPGAs or any specialized hardware coming from Intel, or any specialized hardware like it will come from NVIDIA that are the NVIDIA DPUs, right? But to make the examples of this presentation easy, I'm just going to say GPUs from now on. The first topic is the container device interface. For those who have been tracking how to use GPUs in containers, you know that it has been quite a roadmap to get here, right? It's not that easy even as of today. So we as a community gather and say, like, hey, what if we copy the model of the container networking interface that is also a way that the community kind of like sit down and say, like, okay, there are many ways of doing networking with containers. Let's create a standard. Let's create a standard that follows the OCI implementation and deal with it. Now, for the container device interface is very similar to the container networking interface, where we call a device, and you can define a device where I'm going to show next, and this becomes the responsibility of the vendor, right? So as I said, like this is a joint effort with Intel, NVIDIA, and other hardware vendors. So Intel or NVIDIA should give to you the CDI, the container device interface, and the implementation for the special machines that you have for running containers on that. So as I put, last, vendors are responsible for writing the CDI implementations, right? So this is part of we vendors trying to make it easier for everyone to consume and run containers and Kubernetes on top of specialized hardware. And the good news is this is already introduced in Podman, Cryo, Containerd. Docker is in progress. As you can see, there is a link to the open issues and PRs, but it's getting there. I would say like in the next months, it will be released inside of Docker. And Singularity is already inside Singularity, but for the OCI version of Singularity, right? When you run Singularity -- OCI, you can already start utilizing CDI. So the good news is that we are getting this CDI implementation into all the container runtimes. Here. So this is what a container device implementation, not the interface, would look for a specific type of GPU, right? So here you can see that we are describing one GPU, and for those that have gone like very deep dive into how before CDI we were running GPUs with containers, we were really attaching pre-start hooks to containers and telling the container, hey, before you run, please do this, mount this, try to do this, but it was really like a hack, right? Like a wrapper around how we run containers. With CDI, we are passing this configuration file to the container runtime, and the container runtime will know that, and it will inject this information into the OCI spec. The OCI spec is really a very long JSON that tells the container runtime which folders from the system, which environmental libraries, and which C groups to implement when deploying the container, right? So this becomes a pre-step for running the container and not just a wrapper as we are doing today. So yeah, let me show next. So like as an example, this is how running a container for GPUs looks like today. It's very cumbersome, depending on whatever you're calling, Containerd, Docker, Podman, Cryo, not Singularity. Singularity has a different way. But like for the OCI default container runtimes, you can see that there is a lot of going back and forth and calling some default, like proprietary NVIDIA tools to then call back the container runtime to tell the container runtime to do this or that, depending on the underlying GPU. Once CDI is implemented, you can see that it's very fast, and we just define the CDI implementation. The runtime just read the CDI implementation, mounts whatever it's defined in the YAML that I showed before, and runs the container, right? So we are removing all that wrapper, and we are making it easier. And now everything is going to be maintained inside the container runtimes itself. So we don't depend on this, that we have to update the wrapper of NVIDIA and then the runtime, and sometimes things can break because APIs are not compatible, and I guess some have already run into those problems. By utilizing CDI, we just update CDI, and the container runtime is going to know about this, because CDI now is an OCI standard, right? It's part of the OCI standard. So it becomes just part of how we run containers. Now, we can define very complicated hardware using CDI, now that we don't depend on these weird wrappers that we are using today. But now, how do we expose that to Kubernetes, right? Exposing GPUs to Kubernetes today is really hard, and that's basic GPUs, not to talk about specialized GPUs or FPGAs or any advanced hardware. So we are also working on a solution that is called DRA, the Dynamic Resource Allocation. And it really builds on top of CDI. It's, as we are doing a CDI, kind of like copy the model of the CNI, the Container Networking Interface. DRA is copying the model of persistent volumes. So for those with already some experience in Kubernetes, you know that you can define a volume before starting to run workloads, and then when you're deploying your workloads, you just attach that volume, right? So you can define your volume, how big it is, and the type of volume, if it is going to be an NFS, where it's going to be mounted. Like, you can do a lot of definitions on that volume before starting to utilize the volume. So this is kind of the same, but for devices. So we define a device, and then we can call that device from pods, from workloads. And there are two key concepts to that: resource class and resource claim. The resource class would be the map to what a persistent volume is, right? So when you define the volume, the size, the type, and the resource claim is when you call it from the pod. So today, this is how you mount a GPU, again, a very regular GPU with no special use cases into a pod in Kubernetes. And this is how it will look like by using the array. So wait, I just complicated everyone's life by adding more YAML to something that was easier. But as I was talking with Jordi before the talk, this is for a very simple GPU, but now that we are talking about specialized use cases, imagine that this is a FPGA. Imagine that this is an NVIDIA DPU, right? That this is a very specialized hardware. Imagine that this is something that is coming this year, right? Like new GPUs that have very special features that are not just like using CUDA to run some vectors, right? So this is how it would look like. As I was saying, there is a resource claim template and the resource class name. So the resource class name is when we define the volume type or the device type in this case. And the resource claim template then allows me to call that from the pod, right? So I can call that from the pod. And then I call a GPU. But what if I want to call two GPUs, right? Like my pod can be a very powerful AI training, and I need to have access to two GPUs, not one GPU from my single pod. So today, you can just say two, but with DRA, you can define it like this. Again, this looks more complicated today, but the good idea is that you can even have two types of GPUs. Then we start seeing the limits. Like here, the limit is that Kubernetes would mount two GPUs, whatever GPUs there are in the systems, to your pod. With the new system, you can define two different types of resource claim, and one GPU can be a GPU that is specialized for training, and the other GPU, a GPU that is specialized for inferencing, right? Like we have all the plethora of NVIDIA A, H, and like all the letters, right? So one can be one letter, and the other can be another letter from NVIDIA. So we start to see like the good use cases of having this a little bit more complicated YAML on the right. And now this is a resource class. So it looks very similar to when we are defining a volume, right? That, again, as I said, the quick examples, size, type. Here we can also define like shareable. What if I don't want to share my GPU, or I want to share my GPU for use cases like MPI? Now, this also opens the door for like, I want to have a pool of GPUs, and I want them to be shareable in such a way that pods can share information across the GPUs. Or I can block that, saying no. Like, I don't want pods to be able to share information across GPUs. And this is like more examples on how can I define unique, as I said, like as I put in the example, unique GPU. Imagine FPGAs or DPUs or those GPUs that are coming now to the market that are like just for inferencing or just for training. So I can define a special type of GPUs and mount those special type of GPUs into my pods. So let's here. And also, the good thing about DRA coming from the Kubernetes world is that it is trying, right? This is hardware, but it is trying to take the concept of infrastructure as hardware, and will allow the user, the person consuming the GPUs, to define the GPU also that they want, right? If you know that in your cluster you have many types of GPU, again, just with the example of inferencing and training. So you want to run on a GPU that is more for inferencing, a GPU that is more for training. So as a user, you can define the type of GPU that you want and then use that from your pod. So the strategy MPS is when you want to share for message communication in the GPU. There is a more extended video. We will upload this to the conference webpage if you want to see it, but it's like a 5-10 minutes video on a full demo on sharing GPUs across many pods or one pod consuming a big GPU, but it takes like 10 minutes. And the letter is so small that I'm not going to present it live. Oh, this is trying to click the video, so I have to manually, yeah. The last thing is kind of like competence, like against Vanessa and Claudia, but yeah, we are all trying to do the same. Even Vanessa knows and she likes Q project. So Q project is an upstream project, part of the Kubernetes 6, that is a Kubernetes native queuing controller. And basically, it's a queuing controller. As Vanessa just defined what a controller in Kubernetes is, Q is a project that allows us to define very simple queuing mechanisms in Kubernetes. Before this project, if you wanted to create batch scheduling or queuing in Kubernetes, you had to install something on top. Projects like Project Volcano, projects like Vanessa is working on. There are many upstream projects trying to get batch scheduling into Kubernetes. This is an upstream project that is under the Kubernetes 6 organization. So everyone is contributing to this. Google, I'm contributing to it, and a lot of people. What it does today, it is a job queuing operator. It is very small. It's a very small implementation that allows us to create queues depending on the resources, right? So when I say dependent on the resources, is that I can define a job and attach the job, as I see here, to a queue, right? Queue type main. But when I define the queue, so this is a queue. So when I define the queue, I can give quotas to the queue, right? Kind of like as we do with a Slurm, like everyone queuing on this line, they cannot request more than 3 CPUs. They cannot request more than 4 CPUs, or they will not even be able to get in line, right? So we can control what jobs are requesting on the queue, and then queue that have many queues, right? Like we can define multiple queues, as we see here. Oh, sorry, I clicked. As we see here, we can define names to cluster queues, and we can have multiple cluster queues depending on the projects that I have in my cluster or the teams. I can also define resource flavor. This is a feature very curated for clouds. So if you want to define a resource that is just present on Amazon or Google, but again, I'm running against time, so you can read more about it. Right now, Q is in the version 0.3, and it has many upstream contributors from many companies, and is moving really fast. And the idea is that it stops being a Kubernetes 6, as we see here, 6 project, and it is integrated as part of the upstream Kubernetes as is, right? So you don't have to install it after installing Kubernetes, but it will come inside Kubernetes once you install Kubernetes. The roadmap, we're working on job preemption, scalability improvements. In the last KubeConf, CERN presented that they are running Q, and that they already tested it in a big cluster, so it looks like it scales good, but we want to make more testing before saying that it is like full-scale production ready. But CERN is already like showcasing that it works for them. Again, so I just introduced a lot of abstractions that we're putting on top of Kubernetes, and that will allow us to utilize resources in a more simple way, right? Like we are coming with more complicated and specialized hardware for HPC. We need more abstraction to allow users to get access to these DPUs, FPGAs, and weird GPUs in a very easy way, so they don't have to become like hardware engineers or HPC engineers to be able to use HPC hardware. And why do we want to use cloud in HPC? I really came up with this idea is that the scientific method, if you look from very, very far away, it looks very similar to the DevOps method, right? Like DevOps is just doing code, building, testing, packaging, releasing, and trying back again. Kind of like the scientific method that is observing, researching, doing some testing and experimenting, and trying again until you perfect and optimize your idea. So if this is an abstraction for me on why do we want to take HPC to the cloud. And these are links to more projects that are happening upstream. All of them, we discuss about them in the working group bash. Vanessa also talked about it. So everyone is invited. Please join. It's a bi-weekly call where we chat about all the needs that we have on the cloud for HPC type of workloads. And I think I'm on time. Thank you.
That's awesome. Thank you so much.